this video, we'll further our look at Gauss's law and conductors, and we'll start by looking at the electric field just outside of a conductor. We know that the electric field lines just outside the conductor must end perpendicular to the surface. So the electric field itself, those vectors, must be perpendicular to the surface. Otherwise, the parallel component of the electric field vector would exert a force on that surface charge, and that would violate our electrostatic equilibrium. So when we're talking about a conductor here, we're talking about an isolated conductor. We also know that all the charge on an isolated conductor will distribute itself on the outside surface of the conductor. If the surface is spherical, then that charge will be distributed uniformly. Otherwise, other shapes, that surface charge density varies across the surface, and we can visualize it by showing the field lines landing perpendicular to the surface. So let's use Gauss's law at the surface of a conductor. Now this could be any conductor of any shape, but we're going to consider a section of that conductor that's small enough that it will neglect any curvature, and also such that the surface charge density within that surface is uniform. So we can use then planar symmetry. We'll look at our useful 5-step process. Our first step was to determine a symmetry we could apply, so we're going to use planar symmetry with this strategy of considering a surface section that's small enough, no curvature, and the surface charge density is uniform. So we can look at our Gaussian cylinder or our Gaussian pillbox, and we'll embed that into the surface of our conductor, so that part of, if we look at our cross-sectional view here, one end cap is fully inside the conductor, one end cap fully outside conductor, and the cylinder is perpendicular to the conductor's surface as well, so the central axis of the cylinder. So to find the charge enclosed then, we must sum the electric flux through each of the three cylindrical surfaces. Well, the charge enclosed then, first our first step is we can find the charge enclosed. We know that charge enclosed, we said that surface charge density is going to be uniform over this surface here. So we're just talking about this surface on the surface of the conductor. Well, we made it cylindrical shape, so that area is pi r squared, and the surface charge density is whatever that sigma is. So it's uniform. So that gives us our charge enclosed in terms of surface charge density and in terms of the radius of our Gaussian cylinder. So if we want to find the flux then at each of the three Gaussian surfaces, the left end cap, the right end cap, and the cylindrical surface, we know on the interior end cap here, we'll call that surface 1, since the electric field is 0, then the flux is also 0. So we've determined that. On the curved section here of the cylinder, our electric field is going to be parallel. Electric field is pointing in this direction. There's no electric field in here. We just have electric field out in this portion. But the area vector, our dA, is pointing radially away, and it's going to be everywhere perpendicular to our electric field. So our dot product becomes 0, or E dot dA gives us a 0. The exterior end cap out here, S3, our electric field is perpendicular to the plane of the end cap. So it's parallel then with our area vector, which is also perpendicular to the plane end cap. And if the area is small enough, our electric field will be constant over that plane as well. So we can then use our formula. We can sum up the electric field is 0 here. The dot product, cosine 90 degrees, yields 0. So we have our electric field is uniform. We can pull it out. This ends up with just our EA product, or our electric field times that pi r squared. So we can then apply Gauss's law. Our flux we determined was E times pi r squared. Our charge enclosed we determined was sigma times that same area pi r squared, and then we divide by epsilon naught. So now our electric field is sigma over epsilon naught, and that's true outside the surface of any charged conductor, just outside the surface of any charged conductor. So this shows that we're, it looks like perhaps we're a good distance away, but remember we have a very small Gaussian surface that we're using. If this is a very large planar surface, then our electric field lines will continue to be parallel, and then this would be true, and it shows that the electric field does not change as we move away from the surface. Well, what happens if the excess charge is negative? If the excess charge is negative, then our electric field will be pointing inward. So that difference is that now our dot product yields cosine 180 degrees, or a -1. So if we were to do this in vector notation, we would have to we could apply our Cartesian coordinate system. We could call this direction the z direction. So if it's a positive charge, we'd have E is equal to sigma over epsilon naught k. If it's a negative charge, then we'd have E is equal to negative sigma over epsilon naught k. But that sigma would also be negative. So we don't need to know that. Remember, we're trying to find the electric field. We can also find the electric field direction. So we still can use this same solution, not knowing the direction of the electric field, but since sigma is negative, the negative charge or surface charge density sigma will end up pointing in the negative k direction. So we can find not only the electric field but the electric field direction using this technique. Well, let's compare also this answer. So this is a sigma. Our electric field is sigma over epsilon naught. The magnitude, the direction, we can use whatever that direction is that's perpendicular to the surface. In this case, we define that as our z direction. If sigma is negative, it'll point towards. If sigma is positive, it'll point away. That's just sigma over epsilon naught. So let's compare that to our insulator. When we solved for the insulator using similar techniques, what we solved is we had our electric field was sigma over 2 epsilon naught. And it pointed away from the surface in both directions. So in one direction it would be in the positive k. Here we set up our if this was our z-axis, then this was our y, and this was our x. And we got our positive k and negative k up away in both directions, but we had divided by 2 epsilon naught instead of just divided by epsilon naught. They both have the same discontinuity at the surface of sigma over epsilon naught. So why, in fact, do we end up with that? For an insulator, we get sigma over 2 epsilon naught because we have our electric field pointing in both directions. We have an electric field due to the same surface charge is pointing in both directions. So let's look at a couple of examples. It says, what if the conductive shell has a charged ball inside its cavity? Will there be a charge on the inside surface of the shell? What we saw in the last video, we said an isolated conductor will have no charge on the inside surface of the cavity if there is no charge enclosed. So let's look at an example where there is a charge enclosed. We'll have a ball that has negative 50 elementary charges, or in excess of 50 electrons, and that lies at the center of a hollow spherical metal shell that has a net charge of negative 100 elementary charges, or in excess of 100 electrons. And we want to know what is the charge on the shell's inner surface and what is the charge on the shell's outer surface. Now we can't just assume the inner surface has 0 charge, because we do have a ball lying in the cavity. So let's set up our problem. We have our given. We'll define the charge on the ball, define the charge on the shell. We want to know what is this charge on the inner surface and what is this charge on the outer surface, and we'll well describe that with our diagram. So our approach then we have to use our theory that our electric field is 0 inside an isolated conductor, and we'll use Gauss's law. So we apply Gauss's law. Our flux, that closed integral of E dot dA is equal to Q enclosed over epsilon naught. That's our Gauss's law. In order to apply that, we have to define where are we going to put this Gaussian surface. So let's start by putting this Gaussian surface inside the metal shell, the outside shell. If we do that, then what we're enclosing for charge is we're enclosing this charge on the inside of the shell, and we're enclosing the ball. But what's good reason to do that, we know the electric field there is equal to 0. So the flux is going to be equal to 0. We know the charge enclosed, then we can get a relationship between the QI and the charge on our ball. So with that, we have 0 is equal to negative 50 elementary charges plus QI divided by epsilon naught. So that means that QI must be equal to 50 elementary charges. Or we have an excess of 50 electrons on this ball, so we have a deficit of 50 electrons on the inside of this shell. And that strategy to do that, using Gauss's law, we have to determine where do we put that Gaussian surface. We put it inside the shell because the electric field's 0 there. So we make we simplify our formula and make it easier to solve. So let's then look at, we still have to find the charge on the outer shell. We can put our Gaussian surface then outside, and now we're enclosing a ball. We're enclosing the inner surface, and we're enclosing the outer surface, the charge on the outer surface. So we know the charge on the inner surface, and we know the charge on the ball. So we also know that this shell has an excess of 100 electrons. So we can write two equations for that. We know the charge enclosed is equal to the negative 50E, or the charge on the ball, plus the charge on the shell. The charge on the inner surface and the outer surface, that's just how this negative 100E has become redistributed within this conductor, the polarization that happens. So instead of using Gauss's law, we can just use these two formulas here. And with these two equations, we only have the one unknown, so we can then solve for substitute in Q inner. We can then solve for our Q outer, and that's negative 150E. So we can do a check here. QI plus QO is equal to the negative 100E, and that's equal to the charge on the shell. So that must be true. So that must be true. Our first check is that our QI plus QO is equal to Q shell, and that checks. The other thing we can do is, then further analyze this and evaluate what's happening with the electric field. So we found the inner and outer charges, but what's happening with the electric field, we have the same or equal and opposite charge on this ball as on the inner surface. So if we represent, I guess these are negative charges, so if we represent this negative 50E as 4 negative charges sitting just on the outside surface of this ball, then a positive 50E would be 4 positive charges sitting on the inside surface of this shell. So what's our electric field going to do? It's going to point, it's going to be perpendicular to, if that looks perpendicular, from positive to negative, and it's got to be perpendicular to each of these surfaces, right? So we know what the electric field looks like internally. How about electric field inside the shell is 0, the electric field inside this ball is 0, the electric field outside the ball, our Q outer, is negative 150E. So if this has 4 field lines, this is going to have these 3 times this. So we're going to have 12 charges. So if we put, 1, 2, 3, 4, 5, 6, 7, 8. Whoops, that's too far. I've drawn these off. These charges are sitting right on the outside, right? So we'll have 4. We should end up with 12 of these negative charges, and then our electric field lines again pointing towards. So we'd have 12 electric field lines. So each of these negative charges. It's not an elementary charge. In fact, it's what we represented. Four charges is representing 50 E, so each of these is like what is 12 and a half elementary charges. So we're just doing this to represent what our electric field will look like. It looks like I have drawn it here. So the positive represents a deficit of 12 and a half electrons. You can't have half an electron, but that's what we did. The negative represents an excess, that should say excess of 12 and a half electrons. So if another check we can look at is our shell theorem 2. Our shell theorem 2 says a shell of uniform charge exerts no electrostatic force on a charged particle that is located inside the shell. So if we look at this charged particle inside the shell here, this is the same electric field it would look like whether or not this shell was here. So the shell did not change the electric field produced by this ball of charge. So that's one way to look at it. The other way to look at it, since here it's clear to see since this ball is right in the center, if we looked at these electric field lines as force per unit charge, so they're forces, these forces are all going to cancel with each other. Down cancels up, left cancels with right. So that proves shell theorem 2. Well, what if we moved the charge off center? If we move the charge off center, that would not change the electric field at all externally. Our electric field externally would still have the same 12 electric field lines, because we'd still have the negative 150 E. And all these electric field lines by shell theorem are going to be pointing towards the very center of the shell. But it does change the electric field internally. It changes the electric field internally. Since we're closer over here, these negative charges are going to be more attracted on this side, maybe one here. So our electric field internally, if these are the positive charges, is going to do something like this. Still has to land perpendicular, so let's make sure I get it in the right direction, pointing towards. And there we go. So there's our a very good problem describing what happens when you have a shell of charge with a ball internally. Let's look at one more example. If we want to find the electric field just above the surface of a drum of a photocopy machine, it has a magnitude of electric field given. So we know the electric field. We're going to also assume here the drum is a conductor. And what we want to know is the surface charge density. We know the electric field, we want to know the surface charge density. Well, if it's a conductor, we know the electric field. If the charge is positive, it will be pointing, away. We know it has to be perpendicular here, but if this is, it's going to be going off in this direction over here. But we want to know just above it, right? So just above it, what we showed, what is the electric field right in here? What we showed earlier was the electric field just outside the surface of a conductor, the electric field magnitude, is equal to sigma over epsilon naught. So if we want to know what is sigma, and we're given the magnitude of the electric field, then all we need to do is know what epsilon naught is in order to use this theory. So our epsilon naught is something that we should memorize, 8.85 times 10 to the negative 12, and then we have to come up with what are our units. Well, we can come up with our units right here. This is a Newton per Coulomb. Our E is a Newton per Coulomb. Our sigma is a Coulomb per meter squared. So, well, we also need to know a Newton is a kilogram meter per second squared. So we end up with a kilogram to the negative 1 meter to the negative 3, I believe, and a that's a 3 and a coulomb. And that's going to be a coulomb squared, I guess, because we have 2 coulombs, and then we have our seconds squared. You can check those units to make sure that's correct. So then what is our sigma? Sigma is equal to epsilon naught times E. We can carry that out then to, we should carry it out to 2 significant digits. We use 3 significant digits for epsilon naught. And if I look at my sheet here, this gives me a 2.04 times 10 to the negative 8 coulomb per meter squared, or we can round that to 2 digits. We can write it in engineering notation. It's 20 nanocoulomb per meter squared. So we can check this. Let's just do a check. Let's compare this to a sphere. If we have a sphere of charge, then in the electric field right at the surface, that should look like all the electric field came from the entire charge at the center. So we could actually use Coulomb's law to check this. Let's just compare this to Coulomb's law. Coulomb's law is our 1 over 4 pi epsilon naught Q over R squared. Well, what's Q? Q is equal to our sigma times A, so it's equal to our sigma times 4 pi R squared. So this is equal to 1 over 4 pi epsilon naught times sigma 4 pi R squared divided by R squared. So our squareds cancel, our 4 pi's cancel, and that's just equal to our sigma over epsilon naught. So what we found with Gauss's law, our electric field is equal to sigma over epsilon naught. That's equal to also our K Q over R squared right at the surface of the conductor for the sphere. That's all for this video.